everyone, welcome to my channel. The present topic is Structure of Atom Class 9 Module 4. And in this module, let us learn about isotopes, isobars, electronic configurations of ions, valency. Please subscribe my channel and like and give your comments for betterment of my videos. Isotopes. Let us start with an example. Hydrogen is available with different mass numbers. That is hydrogen 1 hydrogen 1 hydrogen 1 See here, mass number is 1, mass number is 2, mass number is 3. So, atomic number 1 here, 1 here, 1 here. Mass number 1, 2, 3. Right. Now, how do we find the number of neutrons? Number of neutrons equal to A minus Z. See here atomic number is 1, mass number is 1. So here A minus Z, 1 minus 1 equal to 0. That means this does not have any neutron. Coming to here, mass number is 2 here, atomic number 1, therefore it has 1 neutron. This atom has 1 neutron. Coming to here, mass number is 3, atomic number is 1, therefore it is 2. This atom has 2 electrons. Now, observe this. All these are hydrogen atoms. Hydrogen atoms means they are of the same element. Their atomic numbers are same. That means each hydrogen atom has 1 electron and 1 proton. But number of neutrons are different. So, such atoms with same atomic number but having different mass numbers, they are referred as isotopes. So, isotopes are the atoms of same element, with different mass numbers. Okay. Now here there is no neutron. That means the nucleus of this hydrogen atom has only 1 proton. Therefore, this is referred as protium. And its name is deuterium. And this name is tritium. So these are the isotopes of hydrogen. Thus, isotopes of hydrogen only have special names. Each isotope has a special name: protium, deuterium, tritium. Now let us take one more example. Carbon. Isotopes of carbon. C612, C614. So number of neutrons here, number of neutrons equal to A minus Z. What is the atomic number? 6. So here atomic number 6, mass number 12. So number of neutrons equal to A minus Z. This is 12 minus 6 equal to 6. So this isotope has 6 neutrons. Coming to here, number of neutrons equal to mass number is 14. 14 minus 6 equal to 8. So this has 8 electrons. And the mass number of this isotope is a little bit higher than this. Therefore, this is referred as heavier isotope. And this is referred as lighter isotope. Heavier isotope, lighter isotope. This carbon C614 is radioactive in nature. As it is radioactive in nature, this is used in the estimation of age of old wood furniture, old trees, etc. And the process is known as, the process of estimating the age of the wood is referred as carbon dating. Carbon dating. So C614 is used in carbon dating. Now let us see the isotopes of uranium. Uranium has many isotopes. U92, 232, U92, 233, U92, 234, U92, 235, U92, 236, U92, 237, U92, 238. So this uranium with the mass number 238 is naturally occurring isotope, and of course it is abundant in nature. Whereas U235, its percentage, its abundance is only 0.7, but this is very useful isotope. This isotope is used in nuclear reactors as fuel purpose. Isotopes of chlorine. Chlorine has two isotopes, 1735, Cl1735, Cl1737. Therefore it is a heavier isotope, this is lighter isotope. Now let us do a small numerical. Chlorine is available in two isotopes, Cl1735, Cl1737 in the ratio 3:1. What is the average atomic mass of chlorine? Now, average atomic mass is given by atomic mass of first isotope into relative abundance plus average atomic mass of second isotope into relative abundance by total availability of both the isotopes. Now equal to atomic mass of first isotope. Atomic mass of first isotope how much? 35. 35 into, what is the relative abundance in the ratio given? 3 plus atomic mass of second isotope here 37 and the relative abundance in the ratio given as 1. Totally this is 3 plus 1 equal to 4. Okay, now simplify 35 into 3, 105 plus 37 by 4 equal to, how much this is? 12. 142 by 4, this is nothing but 35.5. So average atomic mass of chlorine is 35.5. Now let us discuss one more example. Average atomic mass of a sample of element X is X8 16.2 units. What are the percentages of two isotopes X8 16, X8 18? See here, atomic number is given as 8. So we know that element with atomic number 8 is oxygen. So here X is nothing but oxygen. Average atomic mass of both the isotopes is 16.2, whereas atomic mass of first isotope is 16, atomic mass of second isotope is 18. So let the total percentage of both the isotopes is 100. Now percentage of X16 isotope BX. Then percentage of X18 isotope equal to 100 minus X. So total is 100. If one is X, other one is automatically 100 minus X. Now average atomic mass equal to What is the formula we discussed? Atomic mass, mass 1 into fraction available plus mass 2 into fraction available by 100. So this is the formula. Now let us substitute the values here. So mass 1, what is the mass 1? Relative average atomic mass is 16.2 is equal to mass 1 16 into x. So isotope 16 isotope Vx plus 18 into 100 minus x by 100. So bring this 100 to this side. This becomes 1620 equal to 16x plus this is 1800 minus 18x. Okay. So here bring this side. 1620 minus 1800 equal to minus 2x. So how much is this? 1620 minus 1800. So this is 180 equal to minus 180 equal to minus 2x. Implies x equal to 180 by 2 equal to 90. Therefore, percentage of availability of x8 16 equal to 90, whereas x8 18 equal to 10%. Now let us discuss about isobars. Previously we discussed isotopes. Isotopes are the atoms of same element with different mass numbers. That means isotopes belong to the same element. Now let us say isobars. Isobars means atoms of different elements with same mass numbers. Atoms of different elements with same mass numbers. So let us take an example. Carbon C614 whereas nitrogen 714. See here, atomic number of carbon is 6 here and that of nitrogen is 7. Whereas mass number is 14, mass number is 14. So mass numbers are same but atomic numbers are different, which means they belong to different elements but their mass numbers are same. Now number of neutrons equal to number of neutrons A minus Z. A is 14, 14 minus 6 equal to 8 here, whereas 14 minus 7 equal to 7 here. So what is the reason for isobars? Isobars are available due to the different number of neutrons in their nuclei. Now let us take one more example. Potassium 19, not potassium, argon 1840, whereas calcium 2040. So atomic numbers are different but mass numbers are same, therefore they are isobars. Now let us see the differences between isotopes and isobars. Differences. Isotopes, isobars. They belong to same element. They belong to different elements. Atomic numbers are same, whereas atomic numbers are different. Mass numbers are same. Mass numbers are different. Mass numbers are same. So what does it mean atomic numbers are same is electrons and protons are same in number. Electrons and protons are same in number. Whereas here electrons and protons are different. So these are the differences between isotopes and isobars. Now let us see combining capacity. Combining capacity. Now let us take some examples. Ammonia, NH3, hydrogen chloride, HCl, water, H2O, methane, CH4. See, in all these compounds, hydrogen is combining with other element. Here, one nitrogen atom is combining with 3 hydrogen atoms, one chlorine atom is combining with 1 hydrogen atom, one oxygen atom is combining with 2 hydrogen atoms, one carbon atom is combining with 4 hydrogen atoms. So here the number of hydrogen atoms with which an atom of an element, combine, the number of hydrogen atoms with which an atom of an element can combine is called combining capacity. So CC means combining capacity. Combining capacity of nitrogen in ammonia is 3 because one nitrogen atom is combining with 3 hydrogen atoms. Combining capacity of chlorine in HCl is 1 because one chlorine atom combines with 1 hydrogen atom. Similarly, combining capacity of oxygen in H2O is 2. Combining capacity of carbon in methane is 4. So thus we can find the combining capacity by seeing with how many hydrogen atoms, that is one atom of the given element combines. Combining capacity otherwise is also referred as valency. Combining capacity is also referred as valency. Now let us discuss the valency in terms of electronic configuration. Valency from electronic configuration. Now let us take an example, calcium 2040. What is the configuration? Yesterday in the previous module we discussed that the rules for filling the electrons in orbits around the nucleus. Each orbit can accommodate a maximum of 2n square electrons. That is the first rule. And the other one is outermost shell, or also referred as valence shell, can accommodate a maximum of 8 electrons irrespective of the 2n square rule. So first shell only 2 electrons, that is K shell. Second shell 8 electrons. Third shell 8 electrons M. Up to here 18 electrons are there, still 2 electrons are left. These 2 electrons, suppose if they enter into it, now what happens, it is violating the second rule, that is maximum number of electrons is only 8 in the outermost shell. Therefore the leftover 2 electrons enter into the next shell, that is N shell. So what is the last shell here? Last shell or outermost shell. Last shell or outermost shell is N. How many electrons are there? Number of electrons in outer shell. Number of electrons in outer shell is only 2. Therefore, this is referred as, therefore, number of valence electrons is 2. Right. So we are able to find the number of valence electrons. Then how do you find the valency? So valency is nothing but the number of valence electrons. Valence is nothing but number of valence electrons. So valency of calcium is 2. Valency of potassium is 1 because potassium atomic number 19. So here 2, 8, 8, 1. So valency shell has only 1 electron, therefore valence of potassium is 1. Then let us see chlorine with atomic number 17. Configuration is 2, 8, 7. So valence electrons is 7. So valence of chlorine is 7. Can we take? See here, there are two types of elements. That is, one type of elements having valence electrons 1, 2 and 3. 1, 2 and 3. Here the valence is directly equal to the number of valence electrons. If the atom has 1 valence electron, its valence is 1. If it has 2 electrons, its valence is 2. If it has 3 electrons, the valency is 3. For example, aluminium 13, 2, 8, 3. So here valence electrons is 3. Therefore valence of aluminium is 3. On the other hand, elements with valence electrons 4 or more. In such case, valency equal to 8 minus valence electrons. 8 minus valence electrons. Here, why did we take only 8? Say, in rules for filling electrons, we already said that the second rule as outermost shell or valence shell can accommodate only 8 electrons irrespective of the 2n square rule. That's why 8 should be taken here. For example, chlorine. Chlorine configuration is 2, 8, 7. Therefore, valency of chlorine equal to 8 minus number of valence electrons 7. Therefore, valence of chlorine is 1. Valence is also referred as combining capacity. This combining capacity of chlorine is found as 1 in the previous example when chlorine combines with hydrogen. So, thus, in these cases, valency can be found in this manner. Now, let us take an example of sulfur. Sulfur 16, 2, 8, 6. So, valence electrons 6. Now, valency equal to 8 minus number of valence electrons 6. Therefore, valency of sulfur is 2. Now, let us see the electronic configuration of ions. Electronic configuration of ions. Positive ion or cation. How is it formed? Cation is formed by loss of one or more electrons. Loss of 1 or more electrons. So sodium, let us take an example, sodium. Sodium atomic number 11, right? Configuration is 2, 8, 1. It has valence electrons only 1. Since the valence shell has only 1 electron, this valence electron, that is 1 electron, can be lost very easily. Therefore, after losing electron, sodium Na becomes Na plus. How? Sodium atom, therefore it gives Na, 1 electron is lost. As electron is lost, positive charge is established. Atomic number is same 11, here also 7. So what is the configuration? 2, 8, 1. Here 1 electron is lost. Though atomic number is 11, that means it has 11 protons, but number of electrons is only 10, that is 2, 8. So this is the electronic configuration of Na plus. So in this way you have to learn how to write the electronic configurations of ions. Now let us take one more example, calcium. Calcium atomic number 20, configuration 2882. So what happens? These two electrons are lost. When two electrons are lost, calcium gets 2 units of positive charge, 2 plus. So as 2 electrons are lost, what is the configuration of calcium ion? 2, 8, 8. So this is the electronic configurations of positive ions. On the other hand, electronic configuration of negative ions. Electronic configurations of negative ions. Let us take an example of chlorine 17, 2, 8, 7. What is the number of valence electrons? 7. So chlorine has two options. It may lose 7 electrons or it may gain 1 electron from outside. So generally, which is easier for chlorine? Losing 7 electrons is very difficult. So instead of losing 7 electrons, it gains 1 electron from outside. So chlorine 17, it takes 1 electron from outside, therefore becomes a Cl 17, but 1 electron, negative side indicates 1 electron. So what is the configuration here? 287. So 1 electron is added here. Therefore, what is the configuration? 288. 288. So this is the configuration of a chloride ion. On the other hand, oxygen. Oxygen configuration is 26. So it is a deficient of 2 electrons. O. It takes 2 electrons from outside and becomes O, 2 minus. So already 8 electrons are there and these 2 electrons. Then what is the configuration? This is 2, 8. Now, any atom, if having 8 electrons in valence shell is said to be octet, OCTET, octet. So if an atom has 8 electrons in outermost shell or valence shell, we say that its octet is completed. That means it gets 8 electrons.